Hey everyone, now for a weird one here. Single slit diffraction interference patterns. So remember we looked at the little pattern between your finger and your thumb, and we saw those little bright and dark bands there. It's even something I could catch in a photo a little bit, but you can see it better obviously in real life. Um, and interference pattern there, right? But how is that possible if there's only one light source, only one slit? Well, it's a thing. It actually does happen, right? So this is a single slit interference pattern, and that's a double slit interference pattern. Typically, all you're looking at with a double slit interference pattern is just equally spaced bright bands. You don't necessarily look far enough to see that there's other stuff going on, areas where there's not as much brightness and then more brightness and so on. But this is the pattern that actually exists within the double slit. A lot of times people just don't talk about it, right? Don't look at it, or don't notice it. So how is it possible? How is there interference, right? Well, what do I have here? Notice this. Oh yeah, in this pattern here with a single slit, right? And then you open up another slit, and there's parts in here that were bright that get dark. That's kind of weird, right? So it must be destructive interference, of course, right? So here is two versions of showing that it's showing simulations of it, I should say. So this one here, this is the single slit interference pattern. So if you're changing the width of the slit, you can see the pattern right here, and obviously visualized about how it happens, right? But you can have different versions depending on the widths of the slits and depending on the wavelengths, and so on. So I found the orange is kind of the most visible here, so I had it set at that one. But yeah, there's single slit interference patterns. This one here is interesting. I don't think they designed this applet intending to show the single slit interference pattern in this way, but you can see it starts to try to form, right? But ideally what you'd want is the, I'll show you here in a sec here, this kind of pattern where you have a central maximum, and then you go through another maximum and so on, right? You can see that was starting to kind of form there, but that's the best I could get this applet to simulate that. But yeah, there's your single slit interference pattern, this wide section without all those constructive interference fringes in there, right? So, a two slit interference pattern is really two single slit patterns that are overlapping and interfering, right? So you've got this slit one and slit two overlapping, giving you this. It's something just kind of important to realize. It's super easy to miss that in textbooks and online when you're going through stuff, because the focus is always on the two slits for some reason. I find this one the most interesting though. And this is the nice part about this one, by the way, is if you have a laser, if not, go to like the corner store and buy one for $4. And two pencils with elastic bands holding them together. And usually there's enough of a gap on its own. This video shows the guy putting like a credit card or something between the ends. So that's a card in there. So there's a bit of a space. And you can actually, if he didn't do it in this video, but you can actually squeeze the pencil and adjust the length, the width of the slit. He's going to show the laser pointer through here and then down, right? So when you're watching this, you're going to see the pattern projected onto the wall a bunch of times to get a better video of it. And at some point here, he's going to zoom in on it, the light pattern, there you go. And you can see that's an interference pattern from a single slit between two pencils. Kind of a fun one to do yourself. It's easy to do, right? So hopefully you have the big question in mind, right? How the heck is there diffraction interference, right? Or what? Yeah, interference patterns with a single slit. This should have said interference patterns. Diffraction is leading to it, right? But why is there interference patterns with a single slit? That's really the big question. So why the heck that would be? Let's leave it like that. It's good enough. And so to analyze this, we're going to look through the ideas of it a bit more. But even water waves are seen to do this, right? You get a bit of a nodal area here from a real picture. This is a sort of more of a simulation, but you get nodal areas from water waves. And if you look in this area and on this sort of simulation here, the reason we're going to analyze it out is based on Huygens wavelets again. So instead of this being a continuous wavefront, think of it as a whole bunch of little curves that are all adding up, right, microscopically. And so you can really kind of see it here. Like these are pictures of real ripple tanks, real water wave tanks, right? You get these areas of nodal lines. So we're going to make use of those things again. Oh, I should show this one as well, right here. So this one's just nice. You can, change this to be a single slit pattern and, show the different patterns you get with different slit widths and different wavelengths of light and so on, okay? With a double slit pattern, you're still going to get that same pattern, right? So you have that pattern just with some dark interference, destructive interference in the middle of the bright area. And so what you typically are going to see and hear people talk about is more just, all of the, if you just looked at that, you'd just be like, oh, it's just a bunch of bright bands that are evenly spaced. And that's your double slit pattern, which is really an overlap of two of these, right? And so playing around with that, you can see, if you have a narrower slit, you have more diffraction, interference pattern spreads out, and so on, right? So the driver of this is, of course, diffraction, as the word I had there originally, but it's interference patterns. So I could call this diffraction interference patterns, I suppose. Anyways, but the key part here is, why is there interference patterns, right? Diffraction, we already kind of know what happens. We haven't talked about why yet, by the way, but we will. I suppose with waves, it's just because that's what waves do. But again, the why about why particles would diffract if we look at particle nature of light. But I suppose with this lesson, we're thinking about wave interference. So a little ahead of myself there. We'll get there. So if you have an interference pattern produced on a wall, how would you identify if the pattern is created by a single or a double slit, or the other option, multiple slits? So watch what happens in a situation like, it's good enough like that. If I go to multiple slits, you can see you can get really well-defined bright bands, with multiple slits, with 7 slits. So obviously the math is more complicated, but the more slits I have, the more defined and more contrast you have with those areas where there's brightness. Where when you go down to 2, they widen out. Okay, so there's anyways, so it has a central maximum that's large in comparison to the other ones. It's a single slit, and if it's all even spaces, right, we're looking at double or multiple slits. So we've mentioned that Huygens wavelets are going to be used to analyze this. Let's look through the idea of it. We're not going to do this too thoroughly, too rigorously, but I think it makes sense what we'll do, okay? So in this central area, many pairs of light arrive in phase, lots of equal lengths and so on. So you're getting constructive interference in this bright center section. If you look at, you go off to an angle of a wavelength. I'm going to come back to this one maybe, but because it's analyzed out, I don't know if I want it, which one I want to do first, but this is a full wavelength. And then in the middle, we have a half wavelength, and at the bottom, nothing, of course, right? And so basically you look at, the bottom and the middle, right? Light arriving from here and here is going to be destructive because it's off by half. Light arriving from the middle and the top, off by a half. Basically, you get a bunch of pairs of destructive interference, and so you get your first dark fringe, okay? So that's what this says here. First dark fringe is going to occur at such an angle where you have a wavelength difference here, and it talks about how you have a bunch of pairs of out of phase stuff combining. Okay, so that's the idea of that one. And then if you go to an angle of 3 halves, right, then at 3 halves, you're going to have a bunch of pairs of halves. So halfway length off here, halfway length off there, halfway length off there, and so on. So you're going to have a bunch of dark areas as well. So it ends up being 1/3 of the brightness. If you do the math, you pair them all up and so on, because you have top thirds and bottom thirds canceling out and so on, and then 1/3 of them are constructive. So this first one, you have a 1/3 brightness, but it's a percentage of it, and then and so on and so on. So this analysis, if you did all the details, which I certainly didn't do here, right? But it works. It makes great predictions about the wave property, or about light based on wave properties. So the pattern here of things, we have the values here. Remember, it was, we had the lambda over W, and 3 halves lambda over W, and so on, right? You look at the mathematical pattern for that, and for constructive interference, you can analyze the same kind of thing. You get the 0 and the, again, I'm not doing the details here. I'm just showing you the idea of it. But when you analyze those mathematical patterns, these are the mathematical equations that represent those number patterns. So n for the dark, and m plus 1/2 for the bright. Right? So again, just new equations that can be used. This is for single slit stuff, right? So if you're making an equation sheet to do with all this for easy reference, make sure to point out that these guys are for single slit interference patterns. So we have maybe your first small angle approximation in your science career. So if we have the length L greater, like a lot greater than y, then sine of theta is about the same as tan of theta, right? Because tan is opposite over adjacent, and sine is opposite over hypotenuse. If you stretch this triangle out really far, right? So if we had an angle, a really slight angle, I'll show you here, really slight angle, and I could go even slighter, I suppose, right? Sine is this over the red one. Tan is this over the black one. Well, how different are the red one and the horizontal one? Very little, right? So that's a very classic. You'll see that again and again and again, I'm sure. But yeah, so that is, maybe you've seen a bit of a small angle approximation. It's kind of similar to the one we did in the previous lesson of the infinite, go really far approximation, because obviously it's based on the same thing. But anyways, yeah, so sine of theta is that, and based on the other equations we have previous results and so on, right? And so I'm just showing you the progression of the equations. You end up with this, okay? So for minimas, for dark, and for maxima, and again, single slit interference patterns, okay? For both of them, you've got that. Anyways, yeah, know that the logic of this is, it makes sense and you can use them and so on, not requiring memorization, of course. Just pick out the equations and use them when questions describe a single slit and so on. You get your angle and your numbers and so on. Okay. So example here, when wavelength of light is 680 nanometers shot on through a slit, a single slit, it should say, maybe for emphasis there, but a slit implies a single slit. Patterns created on a screen, such as the first dark fringe, is at an angle of 8.6. What's the width of the slit? So this is the given information, and you pick the equation that has that stuff in it, plug in the numbers, and calculate the answer. Width of the slit, there you go. W for the width of the slit there. A beam of light of an unknown wavelength we're going to figure out, right? So what's the wavelength? Directed at a slit of a known width. The distance from the central maximum to the second dark fringe is 4.2. And so we're going to have an n value of 2. And yeah, we have the length and the n value of 2 if we're using it. I guess we're not using it in this case. Anyways, so there's your information. There's an equation that has that in it, and you plug it in. Oh, there's the 2 in there. There we go. Just wasn't listed for some reason. I would have like to have n equals 2 in there, and it's because you're looking for an equation that has a w and the y2. Remember, this was like x number before. This one they're using y for some reason for the single slit stuff. But yeah, equation, numbers go in, gets you an answer. Calculate the width of the central maximum. Okay, so the width of the central maximum, looking for 2 of these delta y's, right? Delta y is the off to the center, off from the center. And so you'll see here we have delta y, and then it's 2 of those, right? So width of the central maximum. But again, you can obviously go through the file and look through the, press pause and go back and see this. I just don't like having the lesson videos drag on too long. A helium neon laser with a wavelength known value shines through a single slit of a known width, super small width. What's the maximum possible number of minima, like dark bands on the screen? Kind of a weird version, a kind of weird question of this, but it says here, the maximum number, you have to think about the angle you'd go to for diffraction would be 90 degrees. That'd be the maximum. I don't like this question, to be honest, but I mean, I guess it sort of makes sense. Put in the 90 and so on. You're not really going to see that one at 90 degrees, though. That's why I don't like it. It's shining off at such a large angle. But I decided to leave it in the lesson. And yeah, that's it. There's that maximum there. You get a delta y off each side, right? So that's why we did the 2 delta y, if you're confused by that. And questions. So again, very optional practice of using the equations with water waves, but the main focus, of course, using the equations for light. There's only 7 this time, so I don't think there's much reason to skip there. And yeah, so that's it for now. Talk to you later.